All right, I think we're set up.
Fantastic. Thank you so much, Victor. Welcome everyone to Neuroccino on this Monday morning. Today we have a Methods Monday and Victor is presenting to us. And I also want to remind you that this week is already the end of the month. So we have a CNS talk this Thursday at 4 p.m. More info later on that. Without further ado, Victor, if you want to share the link to your paper, we can get started.
Okay, so
lovely.
One thing that I noticed also is you probably would like to go to the Google Scholar form, the research to get the article, because last time I tried to download the PDF from the website, it didn't work. But when I used it on Google Scholar, it did. So wait, I can't see it on your computer now. Okay, I'll do it on my computer. No, that's a bad idea. Oh my God. Why is there no article here?
It's probably opened in a separate window, and if you use 4 fingers and slide on the trackpad, you get the different.
No, it just, maybe I need to access through the institution, but no, because I have it on my computer, but I'm on yours right now. So this is annoying.
Hang on, let me see if I can quickly download it for you.
I can, I think I'll connect with my computer too, and I'll share on my computer. Okay, where is it? I will admit myself.
Recording in progress.
Careful with the echo, you might want to mute the iMac.
Okay. I'm so much unprepared. Sorry about that. So let's get the article now. I should have it in here. And here you go. Where is it now? Here. All right. So the article I want to present you is an article about a new MEG method. So oh, sorry, I'm trying to think straight now that I'm still in the stress. So MEG, magneto, and sorry. And thank you, magnetoencephalography. How do I close that? Like this? Okay. Which was introduced a few years ago. So MEG is not a completely new technology. It's been used for quite some years now, and it's a technology that is used to detect some small variations of magnetic fields due to the neuron firings in the brain. So somewhat like EEG, but with much better precision in terms of spatial resolution. And you can actually, with some mathematical model and such stuff, you can create a 3D model of where the activation is in the brain. So somewhat also like fMRI, but it has a great advantage compared to fMRI is that it has a very like in MEG the time resolution, it's much better than anything that we can have with fMRI, because with fMRI we are not actually looking directly at the neuron activation. We are looking at the hemodynamic response from the neuron activating, and so it's much slower, and that is much slower than directly looking for the magnetic response from the neurons when they fire. And so, okay, so MEG is great for these very high frequency things, but it has a big trouble. It's the same way as, let's try to find an image. So yeah, here, if you can see here, the MEG apparatus, MEG machine is, well, big, not as big as an MRI, but it's big, and it necessitates some well, cryocooling, so some liquid. I think it's not liquid nitrogen, but it's I think it's liquid helium. So very low temperature for superconductivity magnets to have a good detection of what's going on. And so it requires a big machine. It requires you to have your head fixed into the machine, not moving at all. So it's a one size fits all kind of thing, where you have to have the right side, to have the right head, so it can't really be used on small heads, like for example children. And it has also the problem that you need a gap between the detectors and the head, because, well, the detectors are at minus 269 Celsius, so that's very cold. So you need an insulative gap, so you don't hurt the participant. So yeah, it has great values, but also limitations. And I mean, any techniques has this kind of limitations, one or another. But with this new technique, it's using a new kind of detectors that are using a new principle, which is called optically pumped magnetometers, or OPM, sorry, which actually do not require any kind of cryocooling. So basically, it's like small chips. I think you've got an idea. Yeah, small chips like that each one have the capability to record very precisely the very tiny fluctuation in magnetic field that is done when the neuron fires. So this is great. On the technical principle, just for the physics nerd of, if there are some of you like this, for me it was super nice. It's some kind of the physics principle is that you've got a little chamber here in the detector, where there is a vapor of rubidium atom. Yeah, rubidium 87 atoms. And you then send a laser through them, that is a polarized laser, which will pump the atom. Well, I won't go into detail, because actually I wouldn't be able to explain you much about that. But basically, what it does is that it aligns the the atoms, the spin of the atoms, and when all the spin and all the atoms have the spin aligned, actually they stop absorbing the light from the laser. So when they are all in the same direction, the laser will go through them without interference or without interference. Thing is, when you've got some magnetic field changing near them, for example, the neurons firing, it will change the magnetic field, and it will change the direction slightly of the atom in the vapor here. And so, because it's not aligned anymore, it will start to absorb again the light, and the intensity detected will decrease because some of the light will be absorbed by the atom. And so, just by detecting how much light is absorbed here by the detector, you can say, okay, the field is fluctuating, and so you can actually detect this kind of very, very tiny changes in magnetic field. So, well, I mean, there is a few more problems and solutions that they had to find to make this work, but this is the physics principle that I find pretty neat. But of course, it does not come without trouble either, because so here, let me just look at my notes here. So yeah, one of the problems that they have to face is that, well, it's very sensitive to any tiny change in magnetic field, but there is magnetic fields all around. Like every time you have a car moving just by the window, or you have someone actually moving around you, or you have your phone beeping or something, there is magnetic fields going and coming. And so this will be detected and it will mess the recordings. So what they had to do is create a very shielded, magnetic shielded room where they can do all the experiments. So this is something that they have to do to use this kind of thing. And they also have to create an active magnetic shield, which cancel out the magnetic shields from the Earth, because when you are in the classical MEG machine, your head do not move, the machine does not move, which means that the detector does not move compared to the magnetic field of the Earth. But one of the great thing with the new with this new technology is that you can have a lot of detectors that are placed directly onto the head and move and have an ecological relation with an ecological setting to do experiments. So the participant can move around and do stuff while wearing the new MEG machine. And so because its head is moving, it's moving inside of the magnetic field of the Earth. If it's turning like this or like that, it will change the magnetic field perceived by the sensors. So you have to actually remove this magnetic field, thing that you did not have to do when the machine was stationary. So they had to create like that. They put two panels that we can see in the background here to create their own magnetic field, sense the magnetic field around, and cancel it out so that in the middle where you do the experiment, you have actually no magnetic field. So a lot of setups that is quite complicated, but in the end of the day, it allows you to have a very impressive headset that does basically the same thing as the original MEG machine, but which is much lighter, which you can move with that on your head, and which can be adapted to any head. Basically, you can record the signal on babies and people doing exercise. Here we have someone doing ping pong. Here with someone with a reality headset, virtual reality headset, doing an experiment. So all kind of experiments that were not possible before. And it's also possible to do things with patients who have a disease that makes them move a lot or something like that. For example, Parkinson's. To scan someone with Parkinson's disease is always challenging, but with this kind of technology, you could actually do it at least to do a functional scan much easier. They're also talking about scanning people for I'm looking for it, for epilepsy, which can be tricky with fMRI and such, and which may be much better detected and localized, especially in the brain with this technology. So a lot of things possible now, and it seems, if I understood correctly, it's coming to the market kind of soon, because it's the Nature article that is at the that first talked about this method has been published in 2018, I think, and this is more a report about the advances and where we're at and what to expect from this technology. So it's really short to read and a really nice read. And if you're interested, I mean, I encourage you to look it up. And yeah, and that's it. Just for the fun story, actually, I found this this new method through a YouTube channel that I'm really fond of, which is called 60 Symbols. 60 Symbols, which are basically a guy who goes to a university, professors specialized usually in physics or astrophysics or some of such, and ask them question about their work and or a specific thing in physics, and they answer quite well. And so this was one of the last ones, and it really piqued my interest because it was both physics and neuroscience. I'm like, oh, that's cool. And it was a method that I didn't know. So here you go. Now you know.
Lovely. Thank you, Victor. And also thanks for having the dual task, managing, presenting, hosting. I know it's not easy to do. Well done. Thank you. Right. Are there questions in the room? I can see people applauding. People are definitely excited about this new development. Yes, Michelle has the first question.
Thank you, Victor. It's very interesting. I was wondering, how deep can you record the signal in the brain using this method? Can you see, because you spoke about Parkinson's disease, but can you see subcortical structures and change in the magnetic field in subcortical structures?
That's a good question. And that's something that I wondered, and I did not have the time to check, because as I remember, these kind of things are mostly cortical recordings, and I doubt they'll have the precision to get to gray matter nuclei. So I'm sorry, I can't really answer you right now about that, but from my understanding, it's unlikely that they reach that deep.
Okay. Thanks.
Great. If I can jump in, just on the figure that you have up on the screen at the moment, you showed that they can use that new headset to also measure when people are active, like playing ping pong or VR. And I was wondering if motion artifacts are an issue in that case.
I think they were saying, from what I read, that it was much less a problem than they had before, when they were using MEG, because in MEG, in the classical MEG, if you had like a few millimeter of motion artifact, it could mess up a lot of the signal. It's very sensitive to motion. So they are saying that it's still very sensitive to motion, but what they do is actually create, if I understand correctly, a headset that specifically fit to your head using 3D printing, so that you can have a specific headset for you that will fit you well and will reduce as much as possible any kind of motion that you have. I still guess that you can't do shaking, you can't shake your head around and stuff like that, but it's still something that is much better than before.
Sure, but try playing ping pong without moving your head.
Yeah, it's true
that's
that
a challenge.
Here the playing ping pong is basically just playing with a ball on the ping pong racket and doing stuff like that. It's not like playing a match of ping pong. That, to be fair, yeah, it's different.
Sarah, you also had a question.
Yeah, it was like similar than yours and Michelle, so it's like redundant, but I was concerned about the accuracy, the precision, because there are a lot of field potentials in the brain, and I know that the big areas are really interesting. We always like to see, I don't know, the motor cortex or like big areas, but maybe it's only I think not a question, but like in the future, I suppose that they are going to reduce the size of the the chips, no? Because in order to be more precisely, no? Is the bad thing I may see, and also the movement.
Yeah, I think well, they may be able to increase the resolution and to reduce even more the size of the sensors, but if we have to keep in mind that it's not going to be equivalent to a 70 scan in fMRI or something like that. It's way different from the technology. So I don't expect them to get to this kind of precision very soon. I think what they have that is very interesting is more about the temporal resolution and the motion, the availability of doing experiments while moving. That is interesting, but it's true that I don't think they will have a very high accuracy spatial resolution. So you won't have like, oh, look, this a very tiny part of this gyrus is actually lighting up this way in this position. So that means that this. No, I think it's more like, okay, this general area, this gyrus, the whole gyrus is not responding to the specific pattern of activation that we are used to with this very high frequency, which means that it's always a trade-off between right now it's a trade-off between temporal resolution or spatial resolution, and yeah, here it's clearly more about temporal resolution.
Temporal.
Yeah.
Nice.
Victor, can you just recap for us why this is needed in neuroscientific research? Because there's also the push for mobile MRI headsets. Why do we need MEG these days? Well,
MEG these days, for especially this kind of portable MEG, it's portable, not in the sense that it can move out of the lab. It will stay in the lab because it needs a very shielded room and everything. But it will be really useful for studying young children's brain, especially the evolution from very young children to their growth. It will be interesting for many kind of functional study where you want to know exactly how the brain works when you you are moving around and exactly in a more ecological setting. So I don't see that happening anytime soon in fMRI, right? Because even doing task with moving your body and everything in fMRI is still a big no. So it's different. It's new. It's a new thing that is completely, that does not really overlap with what we do in fMRI. So I think it's a good thing to have now. And the fact that it can be used on any type of brain size is also a very big plus. So this is, basically, I think they are mostly interested in studying the children's and the developmental evolution of the brain through the children development and at the functional level. But as I said, they're also interested in epilepsy, and especially they are saying epilepsy in young children. That's what they are focusing on, and that's something that is, I think, very interesting and still hard to study with the technology we had. So
Thank you. Cesare has a question as well.
I want to be like a bit straightforward on this, but it's a big improvement for sure, and it still has to go on the market. But I was wondering if it's going to cost less than the usual Mac.
So I forgot to tell that it's going to be extremely less expensive, like crazily, because a Meg usually is about $2 million, I think.
Exactly.
And this will be a few thousand or 100,000, I don't know exactly, but it's one of the points that they talk about. It's like, it's really less expensive, because actually they did not develop themselves the sensors. It's something that has been created by a US firm recently, and that they adapted to the use for Meg. And so the sensors, the thing that is actually costing, I think, a lot, that might be costing a lot, can be mass produced already. So this is not a problem. That's actually quite a good thing, that this kind of thing here is, you just can buy it off the shelf, basically.
Okay, good. No, because I mean, the more people will use it, the better.
That's true. Yeah, that's true. That's something that I forgot to talk about. But that's a big plus if you have a small lab. Well, one thing also to notice is, like, it's probably cheaper to buy, so it's good for small labs and stuff. But the best also is that it's much cheaper. The upkeep is much cheaper, because with a Meg or an MRI, the upkeep is crazy. You need to refill the helium tank and to have the whole thing running all the time. And here it's just like plug and play, or not plug and play, but plug and use it and then switch it off, and it's fine.
Mm-hmm. Yeah. Thank you.
Tobias also has a question.
I was wondering, did they mention something about applying this to animals? Because that is also a field where data acquiring is oftentimes quite hard. So I could imagine that there are certain things this would enable to measure the first time, basically.
I didn't quite get in the field you're talking about. In what we can use it for?
Like measuring animal brains, because
animals.
there are certain animals you can't just put in every scanner because they are too tall or too much moving and stuff like that.
That's actually a great idea. I don't think they are focusing on that at all, and I don't think they're thinking about it, but this is actually a great idea, because you could create a headset like this for any kind of animal, basically, and that would work. Well, of course not very big animals, because you still have to have a shielded room, and you can't put an elephant in that room. right?
Yeah, don't talk about the elephant in the room.
Exactly. So,
But also not very small, because the size of the,
yeah, but
like maybe a monkey, or maybe a dog.
Make a monkey, a dog, or
Cat.
something like that, it probably would work well. Yeah, there is no reason that you could not do that. You can just train them to wear the helmet, and then when you need to do the experiment, just put the helmet with the sensors, and you do the thing. And yeah, that's actually, I think it's an exciting way that you could use this technology.
I'm going to 3D print a helmet for Artus next time you see him running around with electrodes coming out. Fantastic. That's all we have time for, I'm afraid, today. Thank you so much for presenting and hosting. Well done. Just as I said, a quick reminder, this Thursday we have a CNS talk by Fernando Santos on the emergence of high-order hubs in the human connectome. So do join us Thursday, 4 p.m. for that one. And I wish you an exciting week in science, and see you Thursday. Bye.